Do you ever find yourself questioning the balance between order and disorder in the universe? Well, get ready to dive into the mesmerizing world of chaos theory. This all began with weather. Chaos theory first emerged when Edward Lorenz was performing a weather simulation experiment, and he decided to change all of his input values from 6 to 3 decimal digits. Turns out, it created an entirely new weather simulation. Well, this is because tiny changes in the input actually cause a huge variation in the output. In fact, it's actually easier to predict the orbital period of another planet in another star system 10 million years from now than it is to predict our own weather here on Earth just a month from now. To predict the weather today, we'd have to know the exact position and momentum of every single air particle in the entire universe. This is simply because the weather just has too many factors. I mean, a butterfly flapping its wings can cause a huge change in atmospheric pressure, which can compound over time. Meaning a butterfly that flaps its wings in New Mexico can cause a tornado in Brazil. But not every small change will compound. There is order to this chaos. In fact, there's 3 main ways that a system can be defined as chaotic. Let's consider the logistic map. This is shown by this equation. Let's imagine that we have 2 logistic maps, both with very similar initial conditions, but one with 0.5 and the other with 0.51. Now, even though the initial difference was very small, the iterative nature of these logistical maps will cause the systems to end up in completely different behaviors. Second is topological mixing. But first, we have to understand phase space. Now, phase space is all the potential states that a system can be within. But when a chaotic system is shown in phase space, topological mixing happens, which is when they just become overly intertwined and intermixed, regardless of their initial positions. And third is density of periodic orbits. Periodic orbit is a set of points that follow a specific pattern over time. Each of those have a density. Now, the lower the density, the more chaotic and unpredictable the system becomes. Now, chaos theory is everywhere. Stock market patterns, population dynamic, the weather, or even your milk swirling around in your coffee. None of these seem like chaos at first glance, but it's because patterns emerge from these chaotic systems.